Hello again everybody, and welcome back. This is the 9th video in the Atmel microcontroller programming series. So in this video we're going to take a look at switch debouncing. Let's go ahead and dive right into it. So GIT, MIC, microcontrollers and more, and then we're going to go to here, and then repositories, of course, and then we're looking for this here, Atmel Programming Tutorial 9, Switch Debouncing. So let's start with the circuit today. So we have a number of debounce switch examples, but first we'll breadboard the circuit here. So let's go circuit for switch debouncing examples.png, and we'll go ahead and save it to the desktop. Save target as, and whoops, not to there. Okay, where's desktop? There we go. And take just a second to download, and let's take a look at the circuit. So this is pretty similar to the circuit from the previous programs. The power supply is the same, the power and ground for the chip are the same, and the programming connection is the same. The only difference is here we're going to put a switch on pin 28, and then you can just have that go right to ground. We'll use the internal pull-up resistor, and then we're going to put our 8 LEDs on port D, so PD 0, 1, 2, 3, 4, and then 5, 6, 7, just how we did with the analog to digital conversion circuit. So I'm going to go ahead and pause the video for just a second and breadboard this. Okay, so we have our circuit breadboarded and we have the picture-in-picture going, so let's go ahead and fire up Atmel Studio. And the first program we're going to do today is going to illustrate the purpose of switch debouncing. So here we're going to choose switch without debouncing.c, and then we're going to choose raw, and I'll swing that over to the other screen to copy and paste out of, and then file, new project, and then we'll copy and paste in the name here, so switch without debouncing, and then GCC C executable, and we're using the ATmega 328P. And give Atmel Studio just a moment to make the project here, and then we'll rename main.c. And there we go, and then we'll copy and paste in the code after turning off code folding. That's Control M, Control P to turn off code folding. And there's our program, and once we bring up that io.h file, then these red underlines will disappear. But first let's go ahead and run the program. And hopefully this will illustrate pretty clearly why switch debouncing is necessary. So yes, we know we have to pick a tool, Atmel, ICE, and ISP, and Control F5 again. Okay, so whoops, okay, I forgot to connect the battery there, of course, that's not the greatest. Okay, there we go. And now it's going to be a little more successful here, so Control F5, and then I'll, once the program starts here, I'll go ahead and bring up the code so you can see that as we're going through the example today. So actually, let's take a quick glance at the code first here. So this is pretty similar to the previous projects, and then here we're simply setting our data direction register to set pin 28 to output. Here we're setting our internal pull-up resistor for pin 28. Here we're setting all of port D pins to output, and then we have this endless while loop, of course, here, how we have in our previous programs. And if the switch is pressed here, so that's if bit is clear, remember that's logic low, then we're going to increment the port D LEDs. So if we were not familiar with the concept of switch bouncing or the necessities for it, looking at this circuit, so we're counting up in binary here, so this is 1, this is 2, if both these are on it's 3, then that's 4, if those two are on it's 5, and so on up to this is worth 128 here. So you would think if we pressed the switch once, this would light, we pressed it again, this would light, we pressed it again, these two would light, press it again, this would light, and so on, and we would count up. But we're going to find that that does not at all happen, and I'm just holding the right side of the board here with my other hand to steady it here. My breadboard's a little wobbly. So, whoa, okay, what happened? As you can see, it counted up, what is that, 128 plus 64 plus 32. So just one press there resulted in far more than a count of 1. And there's two reasons for that. One reason for that is that the chip is going around in this infinite while loop here so quickly that it's able to see that one press many times, and therefore count it many times. So the amount of time that that switch is pressed, maybe a 20th of a second, say, or in that range, that doesn't seem like much to us, but the chip is really quick, of course. Remember, even with a relatively slow clock setting here with the internal clock, we're still running at 1 megahertz. So the chip can check that switch state many times in that time, especially since in this while loop it's not doing anything but checking the switch state and then incrementing port D if it finds the switch is pressed. And furthermore, there is the concept of switch bounce, and unfortunately I have sort of an economy oscilloscope. I tried to get a live trace of switch bounce, but my scope was too slow to really get a good one, so we'll just look at one on the internet. So switch bounce, whoops, bounce, not dounce, B-O-U-N-C-E-O-S oscilloscope. And if we go to images here, we'll be able to find plenty, I'm sure. So let's see, we probably want to look at a larger one here. So okay, search tools, size, and let's go larger than 1024-768. And then the second one here, SparkFun. Okay, I always like their site. I do order from them now and then. So let's go ahead and use that one. Any of these images would work fine though. And then we can go ahead and view the image, and it looks like this is from somebody named Kretel at wichita.edu, so thanks to them for this. So if we were to look at a scope trace of our switch press, we would probably see something like this. So the switch is high, of course, in our case. So this switch is logic low, just like ours. So presumably at this point here, it's not pressed. And then when the switch is pressed, the contacts don't immediately meet each other and settle perfectly. They, maybe say the left side of the contact meets first and then bounces a little bit as the right side settles and then back to the left side, etc. So you get this oscillation here while the switch is settling. And then when the switch is finally pressed, you get this. So suppose that you were to look at this oscilloscope trace and forget about software for a moment, but just think in terms of electronics, and somebody was to ask you, at what point would you say that the switch you're actually satisfied that it's pressed? You might say, well, maybe about here. And then suppose somebody was to say to you, well, why would you say at this point here you would consider the switch pressed? Well, you would say something to the effect of, well, here it's kind of going up and down, I'm really not sure about the state, but here it's been low enough for long enough consecutively that as of maybe say this point, I'm convinced that it's pressed. So going back to code now, basically when we're going to debounce a switch in software, we have to do the same thing in code that we just did with our eyes. So well, the most basic way to debounce a switch is just to have a wait. So once you get to this point here and the switch is first pressed, here you just wait for this amount of time, and then you look for another switch press. The problem is that puts a delay in your program, and as we saw in the previous tutorial, multitasking, if your chip is in a delay, it can't do other things as well. I mean, unless you have a whole bunch of fancy interrupts, timers and counters, etc. set up. But even so, it still is oftentimes not something you can get away with in a significant program to put a delay in your main. So the other way to go about it is, each time the switch goes low, you can look for a certain number of consecutive presses, or you can look for an average number of consecutive presses. Like as of here, for example, you could check every so often, say from here to here, you could check the switch maybe 10 times, and you could say if 8 of the last 10 times you checked it, it was pressed, then we'll consider it pressed, something to that effect. But the point is that no matter what the software algorithm is, and there are plenty of switch debouncing algorithms out there, so and a lot of them are pretty elaborate, so it can be kind of confusing looking at them sometimes, but try to always come back to the thought that the whole purpose of a software switch debouncing algorithm is you're just doing in software what you're doing with your eyes when you look at this scope trace. And I should also mention, before we go further in software, it is a legitimate alternative to debounce a switch in hardware, and there are plenty of circuits out there for that. Switch, debounce, circuit, and if we go to images, and the ones that work really well involve either two NAND gates set up effectively as a flip-flop like this, or a Schmidt trigger like this. So here we see Schmidt trigger, flip-flop, Schmidt trigger, Schmidt trigger, Schmidt trigger, Schmidt trigger, flip-flop, Schmidt trigger, flip-flop, flip-flop. You get the idea. There are some, you can even use a 555 timer to do a debounce circuit. Here's another one with a flip-flop, there's a Schmidt trigger, and so on. You can try to do it with just a capacitor and not putting an additional chip on your board. I've tried that and have not had very good success with it. So to put two NAND gates or a Schmidt trigger on your board, that means putting a whole nother chip on your board. And that's inconvenient in pretty much any context. If it's in a prototyping or hobby context, that's going to be unfortunate, because what if you don't have one of those in your bin at the moment? And in a production environment, that's going to be actually even worse, because then you have to tell the project manager, well, okay, we need to add X amount of cost to every single board that we're making a million of, or however many, because I don't want to debounce this in software, so we need to put another chip on the board. That's going to get a lot of resistance. So generally speaking, the movement is toward debouncing in software, so let's go ahead and dive into that today. So we can close out of all this. So the first, we can close out of this project here. And the first debouncing algorithm that we're going to take a look at today is just a simple delay. And you'll see that'll work very well for us. So we're going to choose switch with software debouncing delay .c, so this here, and then I'll go ahead and fire up Atmel Studio and then choose raw and swing this over to the other screen and copy and paste in the name and make a new project as soon as Atmel Studio starts up. There we go, file, new project, and then paste in the name here and choose OK, and our chip is the 328P, and there we go. And as soon as Atmel Studio creates the project for us, we'll go ahead and rename main.c. So rename, there we go, and then we'll copy and paste in the code. And this code is pretty straightforward. It's exactly the same as the previous code, except that we've added this one line here with a delay. So let's go ahead and try it out. Control F5. It's going to tell us to pick a programmer, of course. Yes, that's okay. Atmel ICE, ISP, Control F5 again. And we'll go ahead and try it out now. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. You can see that this counts up very nicely for us. So if you're willing to live with a delay, this is a very good way to do it. It is a concern that depending on the switch, the delay may have to vary, and over the life of the switch, a switch that takes a certain delay when it's new, once the contacts are worn, that may slightly change the delay that's involved, so that's something to keep in mind. But if you can live with the delay in your program and it doesn't hurt anything else, this, as you can see, is a very viable way to do it. So let's take a little bit further of a look, however, at some other debouncing algorithms, because, again, in so many contexts, you cannot get away with a delay for a full fifth of a second. So we'll go ahead and close out of Atmel Studio, and then we will go back to here. And then the second program that we're going to take a look at today is switch with software debouncing no delay. So that's going to be this one here, switch with software debouncing no delay.c, and then raw, and then we'll go ahead and fire up Atmel Studio. And then I'll swing that over to the other screen. And just a moment here while Atmel Studio starts up, then we'll close the start page and file new project and paste in the name. And then we'll choose OK, and OK, whoops, still using the 18 mega 328p. And then we'll change the name of main when it comes up. Just another moment here. And there we go, rename, and now we'll copy and paste in the code. Turn off code folding. And let's take a quick look at our algorithm here. So again, there are different ways to do this. We're going to look at a few more examples later, but this is a pretty basic one. It does not use, everything is done in main here. There is not a timer counter or interrupt of any type used. So the section at the top here is pretty much the same as the previous programs, and then we're including delay as well. Actually, there are no delays in this program, so that's not even necessary, but anyhow, continuing on, so we have our bit is set and bit is clear macros, and then we have number of consecutive presses, 8,250, and yes, you really do have to look for that many consecutive presses, even with only a 1 megahertz clock. That should say megahertz there. Even with only a 1 megahertz clock, you do have to look for that many presses because the chip is really cycling around quickly looking at that switch. And then we're going to have a number of consecutive non-presses of 100, so let's take a look at our algorithm here, and we set up the pins just the same as in the previous program. Then we declare these two variables here, int consecutive presses and int non-consecutive presses. So when we come into our while loop, first we're going to check, is the switch pressed? If it is, we're going to increment consecutive presses. And if our number of consecutive presses count has reached our number that we consider to constitute a press up here, 8,250, and again, these numbers here, 8,250 and 100, are experimentally determined, and of course will vary based on the switch that you're using, as well as the clock speed, and perhaps some other things going on in your circuit as well. And also, if you have other things in your main program, for example, if you have other significant tasks going here, then of course that's going to delay the amount of time until it gets back to doing this again, so then this number especially would be substantially shorter, perhaps far shorter, depending on what else you're doing here in your while loop. But in this simplified case, we do have to use this high of a number. So getting back to our what's going on within our while loop here. So if the switch is pressed, we increment the number of presses, and if it's enough to constitute a press, then we increment port D, and then we re-zero our two counting variables. And okay, the spacing got a little goofed up here due to the copying and pasting in from GitHub. There we go. Okay, so in the case, so that's an if. In the case that the switch was not pressed to begin with, then we're going to increment our consecutive number of non-presses, and if that equals enough to constitute that we're confident the user has had their hand off the switch for long enough that it's not pressed, then we're going to zero the two counting variables. And remember, these are 8,250 and 100 for these two ifs. And then at that point we can simply continue looping in that fashion. So let's go ahead and test it out. And okay, please connect a connected tool. Please choose rather a connected tool, Atmel ICE ISP, and run it again. And we'll find that this works pretty well. 1, 2, 3, 4, 5, 6, 7, 8, and so on. You get the idea. As you can see, that's working quite nicely. The problem with this program is that we are not using a delay. So as you see, we have to check 8,250 times to constitute receiving one switch press. And if our chip was doing significant activities otherwise, that really would be an awful lot of time spent just looking at a switch. So what we're going to do next is we're going to add in a timer. So the next program we're going to look at is switch with software debouncing interrupt. So let's go back here and back one more and switch with software debouncing. Where are you? Switch with software debouncing interrupt. There we go. Fire up Atmel Studio, and then we'll choose raw, and then swing this over to the other screen, and then copy and paste in the name once Atmel Studio comes up here. Start, file, new project, and switch with software debouncing interrupt, and choose OK. And we're using the ATmega 328p, and there we are. And just another moment here, we can change the name of main.c and rename, and then we can copy and paste in the code and turn off code folding. So this is very similar to the previous program, only we've basically just set up a timer to only every so often look at the event of what state the switch is in. So these parts at the top here are the same, except we're including interrupt, of course. And then we have bit is set and bit is clear, our two usual macros, and because we're using a timer and only looking at the switch periodically, we're able to go with a far lower number of consecutive presses of only 75, and then non-consecutive presses is 4. And because this is done in a ISR timer compare event here, which is a separate function, so we have to declare our two consecutive presses and non-consecutive presses variables as global variables. And I should mention here, you always want to use the keyword volatile with global variables when writing Atmel-C, because if you don't, what happens is the compiler essentially goes down main, and if it sees that these aren't used, it may very likely optimize them out, at which point this code here won't do anything if it's dependent on those variables. So that's something to keep in mind. Pretty much always when you're declaring global variables, you want to use the word volatile. So continuing on here, the setup for I/O is the same as the previous programs, and this is going to look very similar to the compare timer example from the timer tutorial. Here we're going to set TCC R0A, so we don't need to set the COM bits, and we don't need to set bit 3 or 2. And then we're also going to set TCC R0B, so we're going to set our wave generation mode bits here, here, and here, and that'll set CTC clear timer on compare match mode. And then we're going to, just purely experimentally, I found that using the chip clock divided by 8 for the scaling here seemed to work pretty well. And then here we have our timer counter 0 interrupt mask register, and we're using compare A, so we're enabling that interrupt, so we don't need to enable the compare B interrupt or the overflow. And experimentally, again, I just determined that setting the compare register to 128 seemed to work out pretty well. You could try more or less, as well as, of course, you could change either of these numbers depending on your switch or depending on the characteristics that you expected the program to have. So then at that point, that pretty much concludes main. We just enable interrupts and jump into our while loop. And then here in the ISR timer, this is basically exactly the same code as the previous program, but just copied and pasted into the timer. So let's go ahead and run it. And we'll find that this works pretty well here. It's going to tell us to pick a programmer. Yes, of course, we know that. Atmel ICE and ISP, Control F5 again. And we'll find that we get some pretty good results here. And it's counting nicely one at a time. Whoops, I accidentally held it down for too long there. That was my fault, not a problem with the program. There we go. And I'm kind of trying to reach around here. Is a little bit of an awkward angle because I'm trying not to disturb the camera. But in any case, you can see that's working pretty well. So let's go ahead and take a look at a final option, and this is going to be the averaging that we had mentioned earlier. So you could look for a number of consecutive presses or consecutive non-presses and then reset your counts, how we've just been doing, or you could declare an array of a certain size and then fill that array with the last however many number of presses, 10, 15, 20, etc. And then you could look at, for example, let's say, why don't we just take a look at the code for the next program. That'll be a more concrete example. So switch with software debouncing interrupt averaging, and then raw, and then we're going to go to start new, and project, and we'll swing this over to the other screen, and then copy and paste in the name, switch with software debouncing interrupt averaging, and there we go. And this is going to be the ATmega 328p still, of course. And when it comes up, we're going to rename main. Just another moment here. Okay, rename, paste that in, and then we can copy and paste in the code. And there we go. So what we're going to do is we're going to declare an array, and again, these have to be global so that the interrupt event can see it. So we're going to have what we're going to call the press array, and we're going to declare that. I just experimentally found that it worked out well to have that to be a size of 13. So once that array is filled with 13 presses and we're looking at it, we're going to say that at least 11 of those have to be presses and no more than 2 can be not press states. And then at that point, we'll consider that the switch was actually pressed. Then you essentially reset everything. So let's just take a quick shoot through the code here. Here's the actual presses array, and as you see, we simply declare that to be this size here and initialize it to 0, of course, and then we have an index that steps through that array so we can keep track of which number we're changing at the moment. So we'll get that to that in the interrupt event momentarily. So here we have our usual setting up our I/O for our pins. And then we have TCCR0A, similar to the previous program, TCCR0B, same thing, and TIMSK0. And then we have our compare register, which just experimentally I started with the same value and didn't end up changing it. You may end up changing this depending on the hardware of your switch or various other things going on in a particular project. And then we're going to enable interrupts, and then we jump into our endless while loop. And here is our slightly more involved but still pretty simple timer function. So we're going to declare a variable just to loop through. We have 2 for loops later on. That's all I is for. And then we have a variable here to keep count of the number of presses in the pressed array. So the first thing that we're going to do is we're going to check if the presses indexes run off the end of the array, and if so, then we're going to drop it back to 0. And then we're going to check if the switch is pressed, then the current index of the presses array we're going to set to 1, and if the switch is not pressed, of course, we're going to set the current index of the presses array to 0. And then we're going to increment the presses index, and again, once this overflows past the end of the array, that's okay because we have this if statement the next time through to knock it back down to 0. So continuing on here, the next thing we're going to do is we're going to loop through the presses array, and we're going to, so if for each spot in the presses array, if it was pressed at that point, it'll be a 1, and if it was not pressed at that point, it'll be a 0. So we're basically just going to sum those numbers up into this variable here, number of presses in press array, and then we're going to check is that greater than or equal to that number from above at the top of our program that we constituted the minimum number of presses out of the number of spots in the press array. And if that is the case, then of course we increment the port D LEDs, and then we cycle through the presses array and reset all the spots to 0. And we're going to see that this works pretty well as well. And it's going to tell us to pick a programmer, of course. Yes, we know that. Atmel ICE, ISP, and Control F5. And we'll just give this a quick test here, and we'll find this works pretty well, just as the previous programs did. So there we go. So this is certainly not a comprehensive example of every single switch debounce algorithm you possibly can have, and again, we didn't even touch on doing it in hardware. There are a lot of options there as well, but hopefully for anybody that's new to the concept of switch bouncing or is just looking for a few quick examples to work with, what we've gone through here today will be helpful. And I'm not sure when I'm going to have the next video out. It's going to be on DC motor control, and then we're going to get into servos from there, and then various different forms of communication, ISP, SPI, USART, and USB, and then I'm planning on doing a motor controller, USB motor control from a desktop computer board for sort of the finale project for this series. But I think first I'm going to take a quick detour and get back to OpenCV videos for a little bit. I'm not really sure on that yet, but anyhow, I'll see everybody in the next one.